Hi everyone, welcome to lesson 20 of the Forces in Space scheme. This one is about circular motion, and this is really hard, and really it's difficult for students and even physics teachers, to be honest, to get your head around. And I remember when I first started teaching A-level physics, even though I have a physics degree, supposedly, I really struggled. I was like, what is going on here? So this is definitely going to be a challenge for Key Stage 3 students. What I would say is, if you teach it in a way that just continues to build on these ideas that we've been developing throughout the scheme of work about how forces affect motion, actually, there's nothing in here that should be too alarming for students. So I think the easiest way of demonstrating this is just to have some sort of object on the end of a piece of string. And there's two lessons on circular motion, one on contact forces, one on non-contact forces. Starting with the one on contact forces, starting with things like tension and friction and the reaction force and so on, is a bit easier because it's a bit more tangible. And then finishing with non-contact forces, it's quite nice because there's a nice link back to what we started this whole unit with, which was the orbits of the planets and moons and satellites and other things in space. But we're going to start by looking at buckets on pieces of string. And again, I would tend to think about this in terms of horizontal motion. When you get to A level, you start having to think about a bucket full of water going round and round and round, and why it is that the water doesn't fall out of the bucket and so on. You've got weight and reaction forces involved in there. It does get a bit complicated. I think the easiest way is just to get something on the end of a piece of string and go around in a circle. You could even do your mouse and just go around like that or something like that. That would be fine. And what we want to do is show students exactly what's going on here. So, firstly, this is going to be the person. You could draw a person if you want. I'm just going to draw it as a little dot, or actually maybe it's a cross. And then what I'm going to do is draw, in fact, let's do that with a ruler. I'm going to draw my piece of string going outwards like that. And then I've got some object, whatever it is, at the end of my piece of string. And I'm going to sketch this circular path of this object as it gets swung around in a circle. So, it's nothing too difficult to visualize at this point. What does get difficult is when we have to think about what forces are acting, and this is where it gets quite counterintuitive. But again, this is a nice example because students, they can do it as well, although obviously make sure you manage behavior in a way that they don't start whacking each other, but they can do it. And what you really want them to feel when they're swinging things around like this is that they are effectively pulling. They're always having to keep the string or the whatever's connecting their hand to the object. They need to keep that tight. They need some tension in there, and lots of them will want to think that there's some sort of force pushing outwards, but in fact, as we'll find out, there's a force pushing inwards. So what I would do is start by showing the direction of the motion at any point. Now, the direction of the motion, the velocity, is always going to be at a tangent to the circle. So it's always going to be in that direction. So if you were to draw the object over here, the velocity would be in that direction, and so on. And this is an interesting one, and circular motion is quite a special case, because what you want them then to think about is, well, okay, it's going in that direction, but in which direction is the force acting? And this is where it's kind of similar to what we're looking at in projectiles, especially when we get to non-contact forces and gravity and so on. We can think, well, okay, clearly this bit of string is exerting a force on this object, whatever it is. And again, if you emphasize to them that actually you're pulling that, you're keeping it tight, then what that means is if you're pulling the object towards you with your hand using that piece of string, then the only force that must be acting is a force here. And as I've said already, and you can say to those guys, any force in a piece of string or whatever it is going to be tension. So in this case, and again, we're ignoring the we're ignoring the vertical plane and we're ignoring drag and things like that. We're given a very simplified account. The point here is that this tension is the only force that's acting on that object. So then, if you were to ask them, well, in what direction is the resultant force on this object? They should be saying to you, well, the resultant force must be acting in that direction, towards the centre of the circle. And then if you were to continue to build that idea and say, well, okay, so in what direction is this thing accelerating? The answer you want to get from students is that it's accelerating in the same direction of the resultant force, as we've seen in every single lesson almost throughout this scheme of work. It must be accelerating in that direction. Now this is mind-blowing, and this is where we're getting really, really far away from our Aristotelian picture, because it's going in that direction, but it's accelerating in that direction. And what we see is, if we do the same exercise, I can see my circle is not the best circle, but anyway, if we do the same exercise going in this direction, when the velocity is in this direction, like this, again, where is the resultant force? Well, it's just the tension in the string. So we go like this. So the direction of acceleration has changed. This is the tension T here, and now it's going in this direction, but still towards the centre of the circle. That would be the A there. Now this is what we need to illustrate to students, is that any object travelling in a circle like this is accelerating towards the centre of that circle. And as I said before, that's really, really counterintuitive. And this idea that it's accelerating is doubly confusing, because what you want them to notice here and here is that the velocity is going to be the same. So it can keep going round and round and round. Sorry, I said the velocity is the same. That's wrong, isn't it? The speed is the same. So it can keep going round and round and round and round at the same speed. But because there's a resultant force, there must be an acceleration, and therefore the velocity must be changing. So hang on. It's going round and round at the same speed, but the velocity must be changing. And again, this is where we get to a really deep conceptual understanding of what velocity is. Well, it's constantly changing because the direction is constantly changing. And that's the point here, is that the direction is always changing. So the force is changing the direction without actually changing the speed. Now, the reason it does that and never changes the speed is because it's always perpendicular. You might not want to go into that level of detail. As long as students get the idea that something can be moving at a constant speed, yet accelerating because it's constantly changing direction, you've given them quite a profound understanding of some difficult physical ideas. So what you will see is some check for understanding questions that just check whether this picture makes sense in their head, and then some more examples where they need to practice. I've drawn all of the examples in the deliberate practice from above, and it's worth emphasising that. You might also, I'm thinking about the cyclist in the velodrome example, it might be helpful for you to draw what it looks like, and you can show them pictures of a velodrome. Velodromes have really steep sides like this, so you might want to draw the cyclist kind of, what does the cyclist look like this, with the handlebars and like that on their bike. And what they need to recognise is that the reason you have that steep banked side on a velodrome is so that you get this reaction force, and I need to think what direction that would be in. It would actually be in that direction, wouldn't it? Because it's the normal reaction force. So if I were to draw it like this, so you get a reaction force, but that effectively gives the cyclist a bit of a push, if we think about resolving the forces, in that direction. And that, towards the centre of the circle here, because the track would go round like this, that is what keeps it accelerating towards the centre of the circle, and it keeps it in the circle rather than spinning outwards. There's loads and loads of misconceptions here. It's a good opportunity for you to tease some of those out of students. And if this lesson goes a bit wrong and it's a bit of a disaster, don't worry, because the main thing is that they're thinking about the concepts. So as long as you get them thinking and really challenging the way they think about motion and forces and so on, then that's a valuable exercise. So we'll finish off this scheme of work in the next video, where we'll be talking about circular motion again, but to do with non-contact forces. And really, that's about gravity.